Satellite navigation systems. Modern civilization operates on an invisible, highly synchronized scaffolding, constructed not of steel or concrete, but of the most precise measurements of time ever conceived by human ingenuity. At the absolute foundation of the global economy, the intricate international logistics network and the sprawling digital communications infrastructure lies the Global Navigation Satellite System, a marvel of engineering that functions as the ultimate high-precision metronome for the planet. For a satellite navigation system to work correctly and provide the seamless positioning data that modern technology demands, it is fundamentally required that the signals broadcast by these orbital assets are transmitted with perfect, uninterrupted synchronization. To achieve this unprecedented level of synchronization across the vast emptiness of space and the chaotic atmosphere of Earth, navigation satellites carry the most stable timekeeping devices ever engineered: atomic clocks. The architecture of satellite navigation relies heavily on rubidium atomic frequency standards and passive hydrogen masers, with cesium atomic clocks serving as primary historical and operational benchmarks for the entire constellation. To understand the profound importance of these devices, one must understand that an atomic clock operates on principles vastly different from any conventional timepiece utilized throughout human history. Instead of relying on the mechanical oscillation of a swinging pendulum or the piezoelectric vibration of a quartz crystal stimulated by an electric current, an atomic clock measures time based on the fundamental quantum mechanical properties of atoms when they transition between different energy states. When a specific type of atom is excited by an external microwave energy source, its outer electrons jump to a higher energy state. Then, as it naturally returns from this excited state to a lower, stable energy state, the atom releases energy at a very precise, immutable frequency that is entirely characteristic of that specific element. This resonant frequency serves as a unique quantum signature that cannot be altered by temperature, physical wear, or the passage of time. For instance, the international scientific definition of a single atomic second, established in 1967, corresponds exactly to 9,192,631,700 counts of the frequency of the microwave energy emitted during the transition between the two hyperfine levels of the ground state of the cesium-133 isotope. On board modern spacecraft, both rubidium and cesium clocks are deployed to ensure redundancy and unparalleled stability. Similar to cesium, rubidium features a single outer electron that can be easily manipulated with microwave radiation. As a sophisticated microwave oscillator sweeps through a specific range of frequencies, rubidium atoms absorb the energy and jump to a higher state precisely when the exact resonant frequency is hit. A complex feedback loop then locks the microwave oscillator precisely to this resonant frequency, creating a continuously stable time base that serves as the heartbeat of the satellite. Because they are relatively small and cost-effective to manufacture, yet far more accurate than electronic clocks, rubidium clocks have become the workhorses of the satellite navigation industry. The stability of these orbital clocks is extraordinary and difficult to comprehend on a human scale. A space-rated rubidium clock is so incredibly stable that it might drift by merely 3 seconds over the course of 1 million years, while passive hydrogen masers, utilized on advanced European spacecraft, can achieve stabilities that would result in the loss of only a single second over 3 million years. This microscopic nanosecond-level stability is the only barrier preventing the entire global logistics network, the international financial system, and modern emergency services from drifting into catastrophic chaos. The global financial services sector relies heavily on the precision timing services provided by these faint satellite signals to achieve exact synchronization with coordinated universal time. High-frequency trading, which accounts for the vast majority of modern financial transactions in global markets, requires a perfectly reliable, authoritative source of time to stamp transactions accurately down to the microsecond. Regulatory bodies around the world have strictly mandated this high-precision timestamping to ensure market integrity, verify the exact chronological sequence of rapid-fire trades, and prevent systemic fraud that could destabilize global economies. Beyond high-frequency automated algorithms, voice transactions for single stock trades, requests for quotes in large procurements, and negotiated auctions all heavily depend on satellite timing to maintain verifiable buyer-seller processes. While the financial sector maintains robust backup systems with holdover capabilities that can sustain transaction logging for up to 30 days during a signal outage, the loss of the ubiquitous, free satellite signal would trigger massive operational costs to implement and maintain non-satellite alternatives. However, while the financial sector might survive a temporary outage, the global logistics and maritime transportation networks face immediate peril without these continuous atomic heartbeats. The global supply chain is deeply integrated with satellite timing and positioning for both terrestrial fleet dispatching and critical maritime navigation. Major ports rely entirely on these highly accurate timing signals to track, organize, and process millions of shipping containers efficiently using automated gantry cranes and tracking databases. Telematics systems in commercial freight fleets use this continuous data stream to optimize delivery routes, avoid real-time traffic congestion, reduce transit times, monitor driver behavior, and minimize fuel consumption, which accounts for up to 10% of total last-mile delivery expenses. If the orbital atomic clocks were to drift, or if the signals were lost entirely, the consequences would manifest as immediate paralysis at major maritime hubs. Without the ability to accurately track containers, ports would instantly congest, resulting in cargo ships queuing for days or even weeks waiting to be unloaded, creating a domino effect that would shatter global supply chains. Out in the open seaways, the loss of these signals would disable the automatic identification system, electronic chart display information systems, and portable pilot units, leading to severe navigation delays of up to 2 days and vastly increased risks of maritime accidents and casualties, particularly among recreational boaters lacking traditional navigation skills. Furthermore, consumer location-based services, which have created trillions of dollars in economic benefits since their introduction, would collapse. Crucially, public safety would be severely impaired, as enhanced 911 services, which provide exact location data to emergency dispatchers to shorten life-saving response times, would become wildly inaccurate. To guarantee that a receiver anywhere on the surface of the Earth, from the densest urban metropolis to the most remote oceanic expanse, can access these vital timing signals, navigation satellites are distributed across medium Earth orbit, forming a complex and perfectly balanced geometric constellation. Positioned at an altitude of approximately 20,200 kilometers, these celestial nodes are fundamentally designed to circle the planet roughly twice every single day. The core architecture of the primary United States system dictates that the satellites be arranged into 6 equally spaced orbital planes surrounding the Earth. Originally designed as a baseline 24-slot constellation with exactly 4 satellites occupying each of the 6 orbital planes, the system has since been expanded through decades of launches and operational adjustments. Modern configurations continuously operate 27 to 31 baseline satellites, maintaining overlapping coverage to ensure that a minimum of 4 distinct satellites remain visible above the horizon from virtually any unobstructed point on the planet at any given moment. Maintaining this perfect geometric spacing, which is critical for continuous global trilateration, requires an advanced understanding of celestial mechanics and the continuous execution of highly complex orbital mathematics by ground controllers. At these extreme altitudes, the satellites are not floating peacefully. Rather, they are subjected to a violent myriad of perturbing physical forces that threaten to continuously push them out of their designated operational slots. Gravitational anomalies play a significant and constant role in altering their paths. The Earth is not a perfect sphere. Its equatorial rotation creates a slight bulge, introducing what aerospace engineers refer to as the J2 perturbation. This equatorial bulge causes a nodal regression rate that subtly alters the satellite's orbital plane over time, dragging the spacecraft away from its ideal mathematical trajectory. Furthermore, the combined gravitational poles of the Moon and the Sun introduce relentless third-body perturbations that continually warp the orbital trajectory, requiring predictive mathematical modeling to anticipate and correct. However, one of the most complex and significant non-gravitational perturbations acting upon these satellites is solar radiation pressure. As countless photons emitted by the Sun traverse the vacuum of space and strike the highly reflective surfaces of the spacecraft, they impart a small but continuous physical momentum. Calculating the precise effect of this pressure requires incredibly intricate computer models that must account for the constantly changing angle of the Sun relative to the satellite, the specific geometric shape and material reflective properties of the spacecraft components, and the periodic eclipses when the satellite passes into the shadow of the Earth. A highly specific and historically frustrating manifestation of non-gravitational perturbation that has confounded aerospace engineers for decades is known as the Y-bias effect. Discovered in the early days of satellite navigation, the Y-bias represents an unpredicted, anomalous acceleration along the axis of the satellite's solar panels. Although its magnitude is minuscule, amounting to less than 1 nanometer per second squared, it accounts for a significant percentage of the non-gravitational forces that must be strictly modeled for precise orbit determination. Historically, engineers proposed various explanations for this drift, including mechanical misalignment of the solar panels, irregular shapes of the spacecraft bus, and differences in timescale rates. However, extensive modern research, particularly utilizing data from the European Galileo constellation, has revealed that this Y-bias is primarily of a thermal origin. Because modern satellites often feature a modular design where payload and platform units are located on opposite panels of the spacecraft body, a severe imbalance in radiated heat occurs. This thermal imbalance results in a difference of roughly 240 watts of radiated power between the opposite radiators, generating a constant, tiny thermal recoil force that perpetually pushes the satellite off its mathematical ideal path, regardless of whether it is in direct sunlight or the Earth's shadow. Intriguingly, researchers have noted that whenever ground controllers activate or deactivate specific onboard electrical subsystems, such as a search and rescue payload or a navigation signal generator, the thermal dissipation instantly changes, directly altering the magnitude of the Y-bias force. Over the course of a single year, uncorrected attitude variations related to this thermal effect and slight solar panel orientation errors can lead to a secular increase in the semi-major axis of the orbit by up to 25 meters, a massive deviation that would ruin positioning accuracy if left uncorrected. To counteract these relentless physical forces and keep the celestial nodes from drifting into collision or leaving massive coverage gaps across the globe, a massive terrestrial infrastructure is required to monitor and command the fleet. The Master Control Station, located at Schriever Space Force Base in Colorado and operated by the 2nd Space Operations Squadron of Space Delta 8, functions continuously, 24 hours a day, 7 days a week, to monitor the exact locations, health, and trajectory of every single satellite in the constellation. Relying on a vast global network of automated monitor stations positioned in locations such as Cave Canaveral, Hawaii, Ascension Island, Diego Garcia, and Kwajalein Island, the ground center gathers raw tracking data. Ground antennas track the satellites from horizon to horizon, allowing supercomputers to compute the precise deviations caused by solar radiation pressure, the Y-bias, and gravitational anomalies. Using sophisticated Kalman-filtered databases, the ground segment generates newly updated ephemeris data and course corrections. These fresh navigation messages are then uploaded via the ground antennas to the satellites, ensuring that the broadcasted orbital positions remain absolutely precise and allowing the spacecraft to fire thrusters when necessary to maintain their perfect geometric spacing in the celestial ballet. Yet, even if the physical trajectory of the spacecraft is maintained with absolute perfection, the precision required to convert nanosecond clock oscillations into accurate geographical coordinates forces satellite navigation systems to confront the fundamental mind-bending nature of the universe. In this highly technical domain, the theories of Albert Einstein are not merely academic textbook physics studied in university halls. They are essential daily software patches required to prevent the entire global navigation system from instantly failing. When the earliest satellite navigation technologies were being developed in the mid-20th century, physicists recognized that placing highly accurate atomic clocks in orbit would subject them to the extreme physical realities described by both special and general relativity. According to the principles of special relativity, time is not an absolute constant, it is relative to the velocity of the observer. Because navigation satellites travel through medium Earth orbit at staggering speeds of approximately 14,000 kilometers per hour relative to receivers on the ground, a phenomenon known as time dilation occurs. From the perspective of a stationary observer on the Earth, the high-velocity atomic clocks aboard the orbiting satellites actually tick more slowly, losing roughly 7 microseconds every single day, due strictly to their tremendous speed. Conversely, the principles of general relativity dictate that time is also deeply affected by the presence of mass and the resulting curvature of spacetime. Clocks that are situated closer to a massive body like the Earth experience a stronger gravitational pull and therefore tick more slowly than clocks positioned further away in a weaker gravitational field. Because the satellites orbit at an altitude of over 20,000 kilometers, they are subjected to a significantly weaker gravitational potential than receivers resting on the Earth's surface. This weaker gravity causes the orbital atomic clocks to run faster by approximately 45 microseconds per day. When these two opposing relativistic phenomena are combined, the net physical effect is that the atomic clocks in space run faster than identical clocks on the ground by exactly 38 microseconds per day. While 38 millionths of a second may appear entirely negligible in the context of daily human activity, in the realm of satellite navigation, it is an absolute ocean of time. Electromagnetic radio signals travel at the speed of light, covering approximately 30 centimeters in a single nanosecond. Therefore, an uncorrected timing discrepancy of 38,000 nanoseconds would result in a ranging calculation error of more than 11 kilometers within a single 24-hour period. If these relativistic effects were simply ignored by engineers, a navigational fix generated by a smartphone or an aircraft would become completely false within just 2 minutes of operation, and errors would continue to accumulate at a devastating rate of 10 to 11 kilometers each day, rendering the entire multi-billion-dollar global infrastructure utterly worthless for navigation in a very short time. To solve this monumental physics problem, the implementation of relativistic corrections was brilliantly divided between pre-launch hardware engineering and continuous software algorithms. To account for the primary 45 microsecond acceleration predicted by general relativity, the atomic clocks were physically adjusted before they were ever loaded onto a rocket. Engineers purposefully designed and tuned the onboard oscillators to tick at a slightly slower frequency than the standard reference clocks kept in ground laboratories. Once the satellite is launched and achieves its designated high-altitude orbit, the reduced gravitational pull naturally accelerates the clock's ticking rate, causing it to perfectly match the frequency of the ground-based reference clocks, neutralizing the primary effect of gravity. However, the dynamic effects of special relativity, which fluctuate slightly based on the specific orbital eccentricity of the satellite and its relative motion as viewed from different locations on the Earth, cannot be entirely resolved by a static hardware offset implemented prior to launch. Furthermore, the Earth's obliteness contributes a very small periodic variation in the satellite clock time, having twice the orbital period and an amplitude of nearly 200 picoseconds. Therefore, the system utilizes a continuous software patch. Every modern consumer receiver is equipped with microprocessing software that dynamically executes a specific user algorithm for clock correction, a process deeply detailed in the system's official interface control documents. By utilizing specific orbital ephemeris data packets transmitted directly from each spacecraft, the receiver's software actively computes the exact relativistic variations required to synchronize the signals mathematically, ensuring that the warping fabric of spacetime does not unravel the precision of global navigation. The historical validation of these corrections stands as one of the most critical moments in modern physics and aerospace engineering. Prior to the launch of the Navigation Technology Satellite 2 on June 23, 1977, there was significant debate and skepticism within segments of the engineering community regarding whether these theoretical relativistic effects would actually manifest in a real-world operational system. To settle the debate, this specific satellite was equipped with the world's first orbiting cesium frequency standard, and a frequency synthesizer was integrated so the clock's rate could be manually adjusted after reaching orbit. During the initial days of the mission, telemetry data collected by tracking stations, particularly the station in Panama, revealed that the uncorrected space clock was exhibiting a massive frequency offset of positive 442.5 parts per trillion relative to the ground clock. After accounting for localized station offsets, the measured deviation matched the predicted relativistic shift within an astonishingly small margin of just 3 parts per trillion, providing absolute empirical verification of Einstein's theories, forever settling the debate and laying the unshakable foundation for the modern global positioning architecture. With atomic timekeeping flawlessly synchronized across the vastness of space, and relativistic deviations entirely neutralized by hardware and software, the fundamental task of determining a user's exact position on Earth is achieved through a beautiful geometric process known as trilateration. It is a common misconception among the general public that satellite navigation relies on triangulation, a method historically used by surveyors that involves measuring the angles between points. In reality, a satellite receiver does not measure angles at all, but rather relies exclusively on the precise measurement of distances. The core principle of trilateration relies on the foundational physics equation where distance is equal to the rate of travel multiplied by the amount of time spent traveling. Because the navigation signals are broadcast as electromagnetic radio waves, their rate of travel is a known constant, the speed of light. Therefore, the receiver simply needs to determine the exact amount of time the radio signal spent traveling from the satellite's antenna in space to the receiver's antenna on the ground. By multiplying this precise transit time by the speed of light, the receiver calculates its exact distance from that specific satellite. However, determining a precise three-dimensional location on the Earth requires multiple intersecting measurements. When a receiver calculates its distance from a single satellite, it establishes that its location could be anywhere on the surface of a massive, invisible sphere in space, with the satellite at the exact center and the radius equal to the calculated distance. Naturally, a single sphere does not provide a location. When a second satellite signal is acquired, a second massive sphere of distance is established. The geometric intersection of these two spheres creates a two-dimensional circle, narrowing the user's potential location to any point along the circumference of that specific circle. The acquisition of a third satellite signal introduces a third expanding sphere. Where all three spheres intersect, the possible locations are mathematically reduced to exactly two distinct points in space, one of which is usually far out in space or deep underground, leaving the true terrestrial location obvious. While three satellites provide the fundamental geometry for a basic position fix, a fourth satellite is absolutely critical to the actual operation of the entire system. Navigation satellites are equipped with multi-million-dollar atomic clocks that maintain perfect time, but consumer receivers, such as smartphones, smartwatches, and vehicle navigation systems, rely on inexpensive, mass-produced quartz clocks that are highly prone to timing biases and drift. Because the transit time of the signal is measured in tiny fractions of a nanosecond, even a microscopic inaccuracy in the receiver's internal quartz clock will cause the calculated spheres of distance to be entirely incorrect, preventing them from cleanly intersecting at a single point. The introduction of the fourth satellite solves this problem through elegant mathematics. The receiver's processor uses the fourth overlapping sphere to execute a complex algebraic resolution that simultaneously pinpoints the exact three-dimensional geographical coordinates, latitude, longitude, and altitude, while instantly calculating and correcting the timing bias of its own internal clock. Through this brilliant mathematical process, the inexpensive receiver in a user's pocket effectively synchronizes its own local time perfectly to the orbital atomic standards, achieving nanosecond precision without the cost of carrying a physical atomic clock. Generating and processing these complex signals involves an intricate chain of digital signal processing. Deep inside the satellite, the highly stable frequency generated by the atomic clock is down-converted to produce specific carrier waves, most notably the L-band frequencies. Superimposed onto these carrier waves are unique pseudo-random noise codes that act as a digital fingerprint, identifying the specific transmitting satellite to the receiver, along with navigation messages containing vital system data. These navigation messages are continuously broadcast at a very slow, reliable rate of 50 bits per second. The legacy transmission consists of a master frame divided into multiple subframes containing ephemeris data, which provides the highly accurate, dynamically corrected orbital position of the broadcasting satellite, and almanac data, which provides the generalized locations and health status of the entire satellite constellation. When these incredibly faint radio signals finally reach the Earth's surface after traveling over 20,000 kilometers, they are captured by the receiver's antenna and passed to the radio frequency front end, where they are amplified and filtered. The receiver's digital signal processing architecture then takes over, assigning each incoming satellite signal to a dedicated processing channel. The receiver attempts to align an internally generated replica of the pseudo-random code with the incoming code from space. Because the satellite is moving at high velocity relative to the receiver, the incoming signal experiences a Doppler shift in frequency, much like the changing pitch of a passing siren. The receiver must implement continuous mathematical tracking loops to accurately follow both the shifting code delay and the Doppler-shifted carrier frequency. Only through the successful correlation of these signals, the mitigation of reflected multipath signals bouncing off buildings, and the complete demodulation of the embedded ephemeris data, can the receiver ultimately execute the trilateration geometry and render a precise position on a digital map. Before these intricate digital messages can reach the antenna of a smartphone or an autonomous vehicle, they must survive a treacherous journey through a massive obstacle, the Earth's atmosphere. This atmospheric speed bump introduces severe distortions and delays that, if left uncorrected by the receiver, would completely corrupt the time-of-flight calculations essential for accurate trilateration. This atmospheric hurdle is divided into two distinctly different layers that require entirely different mathematical mitigation strategies: the ionosphere and the troposphere. The ionosphere is a broad, dynamic region of the upper atmosphere, extending hundreds of kilometers above the surface, characterized by a high concentration of charged particles and free electrons, generated by the violent impact of extreme ultraviolet solar radiation striking atmospheric gases. From the perspective of a radio frequency transmission, the ionosphere acts as a dispersive plasma medium. As the delicate navigation signals pass through this layer, the free electrons interact electromagnetically with the waves, causing the signal propagation speed to slow down significantly. Because the medium is dispersive, the magnitude of the delay is not uniform. It is highly dependent on the frequency of the carrier wave. Specifically, the temporal delay introduced by the ionospheric plasma is inversely proportional to the square of the transmission frequency. This means that lower frequency signals suffer a significantly longer delay than higher frequency signals. For decades, civilian consumer receivers that operated on a single frequency band were forced to rely on generalized broadcast mathematical models, such as the Klobuchar model, to estimate and subtract this delay. While the Klobuchar model represents a pragmatic compromise between computational complexity and accuracy, it can typically correct only about half to 70% of the ionospheric error under quiet space weather conditions, and it struggles immensely to provide accurate corrections during severe geomagnetic storms or periods of high solar activity. However, the dispersive nature of the ionosphere provides its own brilliant mathematical solution for advanced receivers. Modern multi-frequency receivers track multiple broadcast signals simultaneously, such as the L1, L2, and newer L5 bands. By precisely measuring the tiny difference in the arrival times of these distinct frequencies transmitted from the exact same satellite, the receiver's processor can directly calculate the exact quantity of free electrons the signal encountered on its path, and completely, mathematically eliminate the ionospheric delay in real time without relying on generalized models. Once the signal successfully escapes the turbulent ionospheric plasma, it plunges into the troposphere, the dense lower layer of the atmosphere where virtually all terrestrial weather, clouds, and storms occur. Unlike the ionosphere, the troposphere is a non-dispersive medium for microwave signals, meaning it slows all broadcast frequencies equally, rendering the elegant dual-frequency subtraction method entirely useless. Tropospheric delay is composed of two distinct physical elements. The hydrostatic or dry component is caused by standard atmospheric gases such as nitrogen and oxygen, which account for roughly 90% of the delay. Because the physical distribution of these gases is relatively stable and well understood, the hydrostatic delay is highly predictable and can be accurately mitigated by the receiver using standard mathematical algorithms like the Sauce-de Moyen model. The critical challenge for precision navigation lies in the wet component of the tropospheric delay, which is caused entirely by the presence of atmospheric water vapor. Although water vapor accounts for only a small percentage of the total tropospheric delay, it is highly variable over time and geography, dictated entirely by shifting weather patterns, humidity spikes, and temperature gradients in the local environment. To achieve the centimeter-level accuracy demanded by modern applications, next-generation positioning services have transitioned away from relying solely on local radio base stations toward utilizing sophisticated physics-based atmospheric modeling. By synthesizing real-time meteorological data and continuous observations from vast networks of ground stations, dynamic, predictive maps of tropospheric disturbances and water vapor concentrations are generated. These wide-area correction models are then broadcast directly to receivers over the internet or via satellite, allowing them to instantly compensate for the highly variable water vapor delay and achieve unprecedented clarity and stability in their positioning data, completely flattening the atmospheric speed bump. The modern landscape of global navigation has undergone a profound paradigm shift, evolving far beyond the historical monopoly of a single, highly restricted system. To understand this modern era, one must look back to the origins of the technology. Following early experiments with tracking the Doppler shift of the Soviet Sputnik satellite in 1957, the United States developed the transit system, deploying dozens of satellites to provide crewed navigation to nuclear submarines. This eventually led to the development of the Timation program by visionary engineers like Roger Easton and the subsequent launch of the first experimental navigation satellites that would eventually become the modern system. However, throughout the 1980s and 90s, as the constellation became fully operational, the United States military intentionally degraded the accuracy of the civilian signals through a mechanism known as selective availability. This policy was strictly implemented for national security reasons to prevent adversaries from utilizing the highly precise signals to guide munitions. Under selective availability, civilian users were forced to endure an artificial positioning error of roughly 50 to 100 meters. This severely limited the commercial viability of the technology. The paradigm shifted dramatically at midnight on May 1, the year 2000, when President Bill Clinton ordered the permanent termination of selective availability, following recommendations from the Departments of Defense, Transportation, and Commerce. By turning off this artificial degradation, civilian signal accuracy instantly improved tenfold, jumping from 50 meters to approximately 5 meters. This historic liberalization of the signal sparked an absolute explosion in commercial location-based services, revolutionizing in-car navigation, emergency response, surveying, and precision agriculture. This pivotal decision paved the way for the contemporary era where the relentless global pursuit of centimeter-level precision has resulted in the coordinated fusion of multiple global and regional navigation satellite systems. As of the current operational landscape in the year 2026, users no longer rely exclusively on the United States system. The environment is now dominated by the synergistic integration of 4 major global constellations: the American system, the European Union's Galileo, China's Beidou, and Russia's GLONASS, supplemented heavily by regional networks like Japan's QZSS and India's NAVIC. Modern high-precision receivers now feature advanced multi-constellation and multi-frequency chipsets that seamlessly process signals across the L1, L2, and L5 frequency bands simultaneously from dozens of different satellites in view at any given time. This multi-constellation fusion provides massive operational redundancy. In densely built urban canyons surrounded by skyscrapers or beneath heavy forest canopies where signals from a single constellation might be physically obstructed or severely corrupted by multipath reflections, the receiver simply accesses satellites from an entirely different network to maintain an unbroken, highly precise navigational lock. This massive increase in satellite availability has been coupled with the rollout of revolutionary orbital correction data services that eliminate the need for costly terrestrial base station networks. The European Union's Galileo constellation, completely independent and under civilian control, has fully operationalized its high-accuracy service. Operating via the specialized E6-B signal component, this service broadcasts precise orbit, clock, and phase bias corrections directly from space. Without requiring any internet connection or proximity to a local terrestrial reference station, the Galileo high-accuracy service allows compatible receivers to utilize precise point positioning algorithms to achieve an astonishing horizontal accuracy of under 20 centimeters globally. Similarly, China has continuously upgraded its Beidou navigation satellite system, a massive constellation of over 50 active satellites deeply integrated into the global economy. Following recent in-orbit optimizations to enhance spatial signal quality and timing accuracy to within 20 nanoseconds, Beidou has robustly deployed its own precise point positioning service. This service enables users to achieve horizontal positioning accuracies better than 0.3 meters and vertical accuracies superior to 0.6 meters without ground-based augmentation. The availability of these overlapping highly accurate services from different geopolitical entities ensures that industrial sectors, from autonomous vehicular transport and robotic surveying to heavy machinery guidance, have continuous access to sub-meter and centimeter-level data streams. Remarkably, the convergence of these advanced signals and miniaturized processor technologies has completely democratized survey-grade positioning. The integration of dual-frequency and quad-constellation chipsets into mass-market consumer devices has drastically reduced the cost of precision. Everyday smartphones, such as the Xiaomi models tested extensively by researchers, now routinely process complex carrier phase ambiguity calculations, leveraging the combined geometry of all four major constellations to deliver sub-meter accuracy in real time, seamlessly enabling the optimization of smart city planning, public transportation monitoring, and autonomous mobility on a global scale. Despite the astonishing capabilities of modern multi-constellation receivers and the democratization of centimeter-level precision, the very reliance on these incredibly faint radio signals has created a critical systemic vulnerability. As the world becomes increasingly autonomous, with financial markets, drone logistics, power grids, and maritime transport utterly dependent on continuous timing and positioning data, the threat of interference has escalated dramatically. Because satellite signals must travel tens of thousands of kilometers from medium Earth orbit, they reach the Earth's surface with extremely low power levels, often compared to the brightness of a single light bulb viewed from thousands of miles away, making them highly susceptible to intentional disruption. Jamming attacks involve broadcasting powerful radio noise on the exact frequencies used by the constellations, drowning out the legitimate, faint signals from space, and causing receivers to instantly lose their navigational lock, blinding the autonomous systems relying on them. Even more pernicious and dangerous is the threat of spoofing, where malicious actors broadcast highly sophisticated counterfeit satellite signals that actively deceive receivers into calculating a false geographic location or an incorrect time. This form of cyber-physical attack could potentially hijack the routing of autonomous vehicles, divert maritime shipping, or manipulate the microsecond timestamping of financial trades. To counter these rapidly escalating threats in an increasingly contested electromagnetic environment, major architectural overhauls are currently being deployed by aerospace defense contractors. The United States has continuously upgraded its space segment with the introduction of the modern Block 3 and the subsequent Block 3F satellites, currently being manufactured and deployed. These advanced spacecraft, built upon the highly resilient LM-2100 combat bus architecture, feature completely digital navigation payloads, massive solar power arrays, and highly advanced radiation-hardened designs to survive the harsh environment of space. Crucially, the Block 3F satellites are engineered specifically to provide up to 60 times greater anti-jamming capabilities compared to legacy systems, utilizing regional military protection capabilities to ensure that both civilian and allied forces can maintain access to vital position and timing data, even in severely hostile, heavily jammed electromagnetic environments. Furthermore, these new vehicles have the capability of hosting specialized interface software to allow for future on-orbit servicing and capability upgrades, breaking away from the historical limitation of static satellite capabilities. However, the ultimate transition towards a truly hardened, jam-resistant, and dynamically adaptable architecture is being driven by the deployment of Project NTS-3, the National Technology Satellite 3. Launched successfully in November of 2025 aboard the inaugural national security flight of the United Launch Alliance's powerful Vulcan rocket, the NTS-3 represents the very first dedicated experimental navigation satellite system deployed by the United States since the historic launch of NTS-2 nearly 50 years prior. Developed under the strict guidance of the Air Force Research Laboratory and Space Systems Command and built by the aerospace contractor L3 Harris, NTS-3 breaks completely from traditional aerospace design philosophies by serving as a fully digital, modular, and dynamically reprogrammable orbital platform operating at a higher altitude. Historically, once a navigation satellite was launched into the vacuum of space, its signal structures, broadcasting frequencies, and anti-jamming capabilities were permanently set in stone by its physical hardware, making it impossible to adapt to newly developed jamming technologies on the ground. The NTS-3 eliminates this severe limitation by utilizing a state-of-the-art reprogrammable digital signal generator. This groundbreaking technology allows engineers at the master control station to remotely reconfigure the satellite's broadcast parameters while it is operating in orbit, enabling the rapid deployment of entirely new, unpredicted signal structures and customized waveforms to actively evade and defeat targeted jamming attempts as they occur. Furthermore, the system incorporates complex anti-spoofing cryptographic signatures embedded directly into the transmission waveforms, allowing specialized receivers to mathematically verify the absolute authenticity of the signal and actively reject counterfeit data broadcast by malicious actors. The physical broadcasting capabilities of the satellite have also been entirely revolutionized. Rather than relying solely on traditional antennas that blanket the entire Earth with a uniform, low-power signal, NTS-3 features advanced, electronically steered phased array antennas. This incredible innovation permits the satellite to focus powerful, steerable regional beams of multiple frequencies and signal codes directly into highly contested geographic areas, overwhelming local jammers with a concentrated pulse of timing data to punch through the interference. In addition to hardening the space-to-ground communication link, Project NTS-3 is pioneering vital experiments in autonomous on-orbit operations. By integrating highly advanced timing systems and onboard integrity monitoring algorithms, the satellite is designed to independently verify its own orbital parameters and the accuracy of its atomic clocks. Should the spacecraft lose contact with terrestrial ground control stations due to an attack or a systemic failure, it possesses the capability to detect anomalies, generate its own error corrections, and maintain accurate position and timing broadcasts autonomously, ensuring that the constellation remains resilient without human intervention. Through these relentless, highly classified innovations in quantum timekeeping, orbital mechanics, atmospheric modeling, and resilient digital signal processing, humanity continues to secure and evolve the invisible infrastructure that prevents the modern world from grinding to a catastrophic halt, ensuring the high-precision metronomes of global civilization continue to beat with absolute certainty.